I already alluded earlier to the analog between lines in 2 dimensions and planes in 3 dimensions. This is the flat, easy thing to calculate. This is the flat, easy thing to calculate. Another nice, simple object to describe in 2 dimensions is a circle. You can describe it centered at the origin or anywhere else and with any radius. The analog over here in 3 dimensions is a sphere. So we can have a sphere centered at the origin or anywhere else. And just like a circle is nice and easy to represent or to describe, so is a sphere. I actually want to start with the circle and the sphere. So remind me of how we represent a circle with algebra or with symbols, with an equation.
At the origin.
Yeah, centered at the origin.
X squared plus y squared equals 1 or r squared.
Okay, good. This is the unit circle, it's x squared plus y squared is 1. If it has radius r, then it's x squared plus y squared equals r squared. What if this one is centered at the point, let's call it A comma B. And let's say it has radius big R. Do you remember how to represent that?
X minus a squared plus y minus b squared equals r squared.
Good. Now I'm going to ask you and everybody else the hard question. Why? Why does that represent a circle?
You have to adjust. Because the original equation is based on it being center to origin, but in this case it isn't. So
Okay,
you have to adjust for that.
good. I don't understand how to write down equations of circles, and what you just told me gives me some sort of explanation for why that's true, but I still I'm not sure why this equation represents all the points on this circle and no other points. So remember, an equation for a geometric object is an equation that a certain set of points satisfies and no other points satisfy that equation. So only the points on this circle satisfy this equation. Why is that true? Can you think of, you may not have ever been actually told why that's true. Can you think of a reason why that's true? Okay, no problem. Why is this one true? Can you think of a reason why that one's true? Or have you just believed what your teachers told you? Your teachers could all be wrong. Go ahead. Take a shot at it. It's fine. It doesn't lead us anywhere.
Does it have something to do with Pythagoras?
Okay, does it have something to do with Pythagoras? Maybe. So give me what you're thinking about there. What's the connection?
How'd you put it?
So let's take a point here. Let's take the point x comma y on the circle.
So it's a weird way to think of it, but if you're constraining this function with r squared, then x and y, there's only certain values that they can produce that with.
Okay.
And that's just going to be a triangle that fits Pythagoras anywhere on that circle.
Okay. So what I'm hearing him say is, if you think of this equation as having a specific fixed number here, the only points that can make this happen are points that, well, first of all, this looks like the Pythagorean theorem, right? So a squared plus b squared equals c squared. The only points that can satisfy that they all look like this. You make a triangle, a right triangle like this. This is the x value, this is the y value, this is r. So yes, that is exactly why this works. It is from the Pythagorean theorem. We don't have to ask why the Pythagorean theorem is true right now. Can you see that all of the points on this circle will satisfy the Pythagorean theorem? Or at least almost all of them? Which ones might give you questions? Yeah, what about this one, this one, this one, and this one? And then, for example, if we take this one, what would this point actually be if this is the equation of the circle? The x value is 0, the y value is? Negative r, yeah. So definitely it does satisfy that equation. Okay? Does that help you think about why this is true?
They're just shifting, right?
They're just shifting?
And so if
Okay.
it was true here, it should be true there.
If what was true here, it should be true.
If we're happy with x squared plus y squared is r squared, with this weird Pythagorean stuff,
Uh-huh.
well, I guess I'm just saying the way transformations work, minus a minus b are just horizontal. and vertical
Okay,
shifts.
good. One way to think about this is just vertical and horizontal shifts. You should be familiar with the fact that you can replace x with x minus a to shift it to the right a. And same thing with this. If you subtract b from y everywhere in the equation, then you're just shifting the graph up b units. So I buy that, but let's think about it in a little bit more geometric way. Let's assume that, let's not rely on the transformation. Now, we won't spend too much time on this because we're about to leave. What is this height of this triangle? If this is the point x comma y, and this is the point a comma b, and it would have been helpful probably if I drew this above the x-axis. So let's think about it this way. Let's think of b as a positive number. So this is shifted positive a units to the right and positive b units up. What is this height?
Y minus b.
Good. That's y minus b. And what is this base?
X minus a.
Yeah, the way I have it written, it's actually a minus x. So I'm going to write it as absolute value x minus a. We could say the same thing here. It depends really on which point I'm picking on the circle, but this is always absolute value of y minus b. This is always absolute value of x minus a. That's why this works. It's still just a Pythagorean theorem, or you can call this the distance formula. The distance between 2 points uses the Pythagorean theorem. Same thing works for spheres. What do you think is the equation of the sphere centered at the origin?
X squared plus y squared plus z squared equals r squared.
Good. And if this is at ABC, we would just shift it the same way we shifted with circles. We'll stop there.